Hello, everyone, and welcome to the Newark Museum of Art's virtual Ask an Astronomer program. My name is Mary Hiller, and today we are joined by Dr. Ryan McDonald of the Carl Sagan Institute at Cornell University, who will tell us all about the amazing James Webb Space Telescope set to launch in December and how it ties to his research in exoplanet studies. We are also joined by Shelley from Language Years, who will be providing ASL interpretation throughout the program, Rebecca from Automated Sync, who is providing our closed captioning, and Imani Lee Hector, our program producer here at the Newark Museum of Art. Before we begin, we'd like to thank those who help make our programs possible. Thank you to the New Jersey Department of Community Affairs, the National Aeronautics and Space Administration, the Space Telescope Science Institute, and the National Institute for STEM Education. So today it is my pleasure to introduce Dr. Ryan McDonald. Dr. McDonald is a research associate at Cornell University studying exoplanet atmospheres. He will be leading one of the James Webb Space Telescope exoplanet programs, as well as being heavily involved in analyzing observations of exoplanet atmospheres with the James Webb Space Telescope. This will cover the full range from hot, giant planets to habitable zone rocky planets. So if you have any questions for Dr. McDonald, you can type them into the Q&A section on Zoom or in the comments section on Facebook at any time during the presentation. We will take time to answer questions at the end of Dr. McDonald's presentation. So without further ado, Dr. McDonald, the stage is yours.
Thank you very much for the nice introduction, Mary, and a very good evening to all of you today. I'm incredibly excited to be able to tell you a little bit about NASA's new flagship telescope, the James Webb Space Telescope, that will be launching beyond Earth this December, on December 18th. Because when I think back to what first got me involved in astronomy and interested as a kid, it was the question of whether we are alone in the universe. James Webb is the very first space telescope that will be sensitive enough to search for signs of alien life beyond our own planet. That's not the only science that it's going to do, but that's what originally got me interested in astronomy. And so it's so incredible that we're just about to reach the point where we can answer this question. So in my talk today, firstly, I'll talk a little bit about why we need the James Webb Space Telescope and how it came about. We'll then look into why James Webb is a telescope that will focus on observing the infrared region of light. We'll then look at all of the incredible science questions that James Webb is going to enable us to answer about our universe. And then in the last part of my talk, I will briefly look at some of the engineering behind what made this mission actually happen. So why do we need the James Webb Space Telescope, or indeed any telescope in space? In short, the problem is our own atmosphere. Of course, our atmosphere is fantastic for enabling us to breathe and life to exist, but the gases in our atmosphere stop many colors of light from reaching our surface. So the colors of the rainbow that we have evolved to be able to see are just a very small part of the full range of colors of light available. There are other colors like infrared, which is redder than red, ultraviolet, which is even more energetic than violet light. There are gamma rays, there are microwaves. Just what we can see with our eyes is only the tip of the surface. So to study the universe in these colors of light that we can't see ourselves, starting in the 1990s, NASA launched a fleet of great observatories into orbit to study the universe. Perhaps the most famous is the Hubble Space Telescope, launched in 1990 and still operating to this day, that has yielded fantastic images of our universe. Hubble can see with the same colors we use with our own eyes. It can also see a little bit of the ultraviolet and the infrared. Chandra was specialized in looking at high energy processes in our universe, that emit X-rays, incredibly energetic forms of light. While the Spitzer Space Telescope, that unfortunately ended its life last year, focused on observing in the infrared. So let's take a look at some of the things about our universe that these previous telescopes have told us. So here I have 4 images that show some of the objects in our universe that we have been able to study, and these are all real photographs. So in the top left, we have an X-ray image from Chandra of the Crab Nebula. So around about 1,000 years ago, in 1054 AD, Chinese astronomers saw a new star appear in the nighttime sky. But this wasn't just a star, this was an explosion. It was a star reaching the end of its life and undergoing what we call a supernova explosion. The Crab Nebula is the leftover dust and gas from this explosion that has continued to spread out over the last 1,000 years. So this is zoomed in right at the center of the Crab Nebula and is showing that in the middle there is a hot object called a pulsar that is the leftover core of this ancient dead star. And it's essentially gobbling up remaining gas and heating it up to such high temperatures that they shine in X-rays. In the top right is a star called Zeta Ophiuchii, and this star is actually sending out powerful winds into space that interact with the surrounding gas to produce this red region that looks a little bit like if you've ever been on a boat and looked at the surface of water, you'll see ripples spreading out. These are ripples in the gas between the stars produced by the light from this energetic star. In the bottom right is another nebula, in this case in visible light taken by the Hubble Space Telescope. This is, again, the leftover remnants of a long dead star that exploded 7,000 years ago. And in the bottom right is a pair of 2 galaxies that are in the process of spiraling together and merging. These antennae galaxies are about 45 million light years away from Earth. And what's particularly beautiful about this image is that it combines the light from Chandra, Hubble, and Spitzer. So the blue light we see here is X-rays being emitted by really hot gas. The gold and brown colors is the light we see with our own eyes, taken by Hubble. And the red color is dust seen in the infrared by Spitzer. So all of these are the relatively nearby universe, though. We have also learned from existing telescopes what is there much further out in our universe. So this is a very famous image called the Hubble Ultra Deep Field that was taken in 2014. The Hubble Space Telescope pointed at a single tiny patch of sky that appears to our eyes to be completely empty. And what it found after staring for 25 days is that every part of our universe is far from empty. There are galaxies in every direction that we can see in this image here. And each one of these galaxies can contain hundreds of billions of stars and planets of their own. So our universe is incredibly crowded and there is a lot going on out there. But so why do we need another space telescope? What can we learn that we don't already know? Well, even when we look in an image like this, we can't see all the way back to the very first stars and galaxies in our universe. We can see quite far. We can see back 13.4 billion years. But the problem is that when stars and galaxies are first born, they shine in very energetic ultraviolet light. And as that light has gradually traveled towards us over the last 14 billion years, the universe itself has actually grown. It's expanded like a balloon. And when light travels through space that's expanding, it stretches out the wavelength of light, making it less energetic. So the ultraviolet light from the very first stars and galaxies has stretched out and is now infrared light that is just too low energy for us to see with Hubble. So what we need is a telescope that can specialize in looking in the infrared to see those very first stars and galaxies. And that will be where James Webb will come in. So let's take a look at this in a little bit more detail. So why do we care about the infrared, and what can it tell us that we don't already know? So let's take a look at visible light that we see with our own eyes, with this nice picture here of a trio of meerkats and a freshwater crocodile on the right there. We can learn a lot in visible light. So we can see that we have fur on the left while we have scales on the right. We can tell different colors, tell us something about these animals. But if we look at the same animals in the infrared, we see a very different picture. So the meerkats appear to be glowing in the infrared because they are warm-blooded animals. And the higher temperature an object is, the more infrared light it emits. While the cold-blooded crocodiles don't shine as much in the infrared and so appear much darker. So by looking at objects in the infrared, we can learn what temperature the objects are. And this applies to both animals, our own bodies, and indeed to the entire universe itself. So this diagram here shows the full range of colors of light that we call the electromagnetic spectrum. So the colors we can see with our own eyes, the visible, is actually just a tiny fraction of all the colors available. So while Hubble has been fantastic at observing visible light and a little bit of ultraviolet and infrared, James Webb will specialize in observing the majority of the infrared range of light. So let's take a look at what we can do in astronomy with the infrared. So this image on the left here is showing a real Hubble photograph of the pillars of creation in the Eagle Nebula. And we can see that these three pillars are essentially just clouds of dust floating out in space, many hundreds of light years across. But we can't see through the dust with the light we see with our own eyes. But if we change to the infrared, this second image is also taken by Hubble, but just in the very beginning of the infrared region, which we call the near infrared, just beyond what our eyes can see. And in this case, we can see through the dust to see stars both behind the pillars and indeed baby stars hiding inside the pillars that we wouldn't have been able to know existed if we were just looking in visible light. If we go even further into the infrared, into the mid-infrared, then we can see the thermal emission from the dust itself. So the first image tells us how much dust there is and where it is. The second one lets us see through the dust. And the third one tells us how hot the dust is. These are all complementary pieces of information that can tell us about objects throughout our universe. So with that, let's take a look at some of the things that we are going to learn about our universe with the James Webb Space Telescope. So I already alluded to how Webb will let us see back to the very beginnings of stars and galaxies in our universe. So our current understanding is that around about 13.5 billion years ago, our universe was filled with hydrogen gas. When the very first stars turned on, they ignited their nuclear engines. They suddenly shined outwards with high energy light. And that caused an event that we term reionization. It's where the hydrogen gas lost electrons, and essentially that allowed light to be able to travel through the universe. The universe is opaque if there is just hydrogen gas there. So these first baby stars then started collecting together under gravity, forming the first galaxies. And all the while, these galaxies continued to shine with light, creating these bubbles in our universe where light could just travel and the universe was transparent. Over time, the galaxies got larger and larger, the bubbles expanded, until eventually the entire universe became transparent, as we see it today, where space just appears to be black and empty. So we have a decent theoretical understanding of this process, but because we haven't been able to observe the very first stars and galaxies, we don't really know the precise times at which these different events happened. And that will be what James Webb will be able to tell us by seeing these very first baby stars and galaxies. We have already been able to see some quite young galaxies with Hubble. This little blob that we see here is a galaxy that formed around about 400 million years after the Big Bang. It's called GNZ11. So Webb will let us see even older galaxies than this, the very first ones that formed in our universe. And by studying galaxies both near to us and far, we can exploit the cool phenomenon that astronomy is essentially a time machine. When we look at an object that is 13 billion light years away, the light was emitted 13 billion years in the past. So by looking further and further into our universe, we can see back in time. So by looking at galaxies at different distances, we will be able to build up a picture of how galaxies form, how they evolve, and how they reach the mature state that we see today. Webb will not only tell us about galaxies, it will also tell us about these incredible objects at the center of galaxies called black holes. So in our own galaxy, because Webb observes in the infrared, it will be able to peer through the dust towards the center of our galaxy and study the black hole that is right at the middle, called Sagittarius A star. It will also be able to look at the black holes at the center of nearby galaxies, like the Andromeda galaxy. And the way that it will do that is that it will look at clouds of gas and stars at the center of those galaxies and measure how fast they're moving. And by doing that, we can actually weigh how much a black hole is without even being able to see the black hole directly, which is really cool. So that's our nearby universe. But we know that in the very early universe, black holes were far more deadly than what they are today. This artist concept is of an object called a quasar, which were very common in the early universe. Essentially, this is a black hole that is gobbling up entire stars. And as it feeds on these stars, it produces these incredibly energetic jets of radiation. A quasar can be billions of times heavier than our own sun and outshine the entire galaxy that it exists in. So Webb will help us to figure out what came first. Did black holes exist first and then they collected gas to form galaxies? Or did galaxies appear first and then when the gas collected, it formed black holes? We don't know at the moment, but Webb will help us to figure this out. Besides galaxies and black holes, Webb will also tell us a lot more about stars, how they're born, how long they live for, how they evolve, and how they come to the end of their lives. So on the left here, for example, in the visible light, we see a dusty star-forming region where baby stars are forming. And the infrared lets us see inside these clouds to see where these so-called protostars are. And this can also tell us about planets that are forming around these stars as well, and the kind of material available to form planets. So besides just taking images of our universe, one of the most scientifically important things that Webb can do is that it can observe many different colors and slice up the colors into very small regions. So when we look at tiny increments of light, we can use a clever fact of nature that different molecules and atoms have a different preference for what colors of light they absorb. So by finally looking at all the different colors of light that exist in a cloud where stars are forming, for example, by detecting these molecules, we can learn about what the ingredients are that are available to form stars and planets, and even the ingredients available for life to start in our universe. But it's not just the distant universe that Webb will tell us about. We can even observe the planets in our own solar system. So here is an image of Jupiter seen in the infrared. And that lets us peer beneath the top clouds of Jupiter and see the deep weather systems present on all of the giant planets to help unlock what is going on beneath the clouds. We will also be able to look at Mars with Webb and monitor dust conditions on Mars and try and figure out what it might be like one day to live on the red planet. But the final area that I want to tell you about is the focus of my own research, exoplanet atmospheres, because we are going to learn an incredible amount about these planets around other stars with the James Webb Space Telescope. So I use in my own research a technique called transmission spectroscopy. The idea behind it is that we watch a planet pass in front of its star, and we look at this event in multiple colors. So if we see a planet at a color of light where the atmosphere absorbs all of that color, the planet appears to be slightly larger, like we see with this orange color here. But if we look at a color where the atmosphere is clear, it will appear to be smaller. And because we know from laboratory measurements on Earth what the precise colors or wavelengths of light are that each molecule absorbs, the chemical fingerprint of each molecule, if you will, we can figure out from how large the planet is at different colors precisely what molecules are hiding in the atmosphere. So some things that I will use that for in my own research is first to look at incredibly hot giant planets. We call these hot Jupiters. They are around about the size of Jupiter, but they orbit 10 times closer than Mercury. So they can be many thousands of degrees in temperature. We think these exotic worlds can have clouds made of rubies and sapphires, have molecules that we have never even seen in our own solar system, like titanium oxide. So we're really excited to study planets that we don't even have in our own solar system. By measuring how much of each molecule there is in the atmosphere, we want to be able to figure out how planets themselves formed. So for example, by measuring how much water there is in a planet's atmosphere, we can figure out how much icy material, like comets, were collected by the planet as it formed. But this is an area that I'm particularly excited by because this is the focus of my own program on James Webb. I remember as a kid wanting to know what will happen to the Earth after the sun dies. And it turns out that we still don't even know. We know that Mercury and Venus will be devoured by the sun when it expands and becomes a red giant. But we still don't know what will happen to Earth. But last year, we found for the first time an intact giant planet around a white dwarf star, which is what our own sun will one day become. And this tells us that planets can survive the death of their star. So I will be using Webb to measure what the atmosphere of this planet is made of to try and figure out how it survived the death of its star. And we hope to use that to figure out whether the Earth itself could survive the death of our sun. So keep an eye out and we'll get the results from this out as soon as we can. But the last area that I will also be involved in, and this is particularly exciting because this is what got me interested in astronomy as a kid, we will be able to search for signs of life for the first time on rocky planets around other stars. This is an artist concept of the planet TRAPPIST-1e that I will be using James Webb to observe in the next 2 years. We are planning to use Webb to search for signs of gases that can only be produced in large quantities by life, molecules like methane and ozone. And if we can detect these biosignatures, we may finally know that we are not alone in the universe. So in the last part of my talk, I'm going to tell you a little bit about the engineering of Webb and how this incredible mission came to be. So Webb itself has a large sun shield at the base that keeps the telescope cool in space and a mirror that we see at the top. Compared to the Hubble Space Telescope on the right, Webb has a much larger mirror, and that means it's much more sensitive to distant objects in our universe because it can collect much more light in every hour that it is observing. So what's particularly remarkable is how long Webb has been planned. So planning for this mission began in 1989, the year before Hubble launched in 1990. Construction on the telescope started in 2002, and it has taken nearly 20 years to reach this point. So you might wonder, why has it taken so long to build this telescope? So in short, the mission was so ambitious that much of the technology required to meet our science goals simply did not exist in the 2000s and had to be created along the way. So, for example, the specialized optics to align the mirrors present on Webb, the materials for the sun shield to keep the telescope cool, the computing necessary inside the telescope, the precise scientific instruments on board. It took a very long time to develop this. But perhaps the hardest engineering challenge is that the telescope itself is just too large to fit inside rockets. So it has to fold up like origami to fit within the 5-meter payload fairing that we can fit on top of existing rockets. And this origami procedure and the unfolding that will take place once Webb is in space requires everything to go perfect, since we can't send astronauts up to where Webb will be going beyond the moon. I'll talk about that a little bit more in a few moments. So here we see Webb's mirror compared to Hubble again. And you'll notice that Webb has this kind of hexagonal honeycomb type pattern. Because we need these mirrors to be incredibly cold so that we are only seeing the infrared light from space and not that light emitted from the telescope itself, we need mirrors that are incredibly strong and stable. So the mirrors on Webb are made of beryllium, which is 6 times stronger than steel and 2/3 the density of aluminium. And on top of these beryllium mirrors, we have a layer of gold that is just 1,000 atoms thick. The reason that we use gold is that it's very good at reflecting infrared light, so it's perfect for an infrared mirror. So I've mentioned a few times spectroscopy, which is one of the key techniques that we have in our astronomer toolkits. What Webb does with its various instruments is it observes the light from a distant object, and it uses devices called spectrographs to spread out the light into many different colors. And what we see when we do this is that not all colors of light are present. We can see that some colors are missing. And this is because of the chemical composition of the object that emitted the light. So depending on the gases present in a planet's atmosphere or in a distant galaxy, the spectrum will be different. So spectroscopy is the key tool that we use to measure what objects in our universe are made of without being able to go there. Webb has 4 spectrographs. I won't go into these in too much detail, but suffice to say that each of the spectrographs has been adapted to a very specific scientific goal. So some of them are able to chop up light much more finely in terms of the different colors than other instruments. The mirror instrument in particular is focused at observing much further out into the infrared than the other three instruments that can also observe a little bit of red light as well as the infrared. I mentioned that Webb is going out much deeper into space than Hubble. While Hubble is in a low orbit around the Earth, Webb is going out beyond the Moon to a special place called the L2 Lagrange point. This is a location in space where the gravity of the Earth and Sun cancel out. So the telescope can just sit there and be very stable. Webb will actually go in a small orbit around this Lagrange point that we call a halo orbit. The reason why we're taking Webb out so far is because we don't want it to get contaminated by all of the infrared light that the Earth, the Moon, and the Sun emits. We still have to deal with infrared light from the Sun, and the way we do that is via the sun shield at the base of Webb. So these 5 layers in the sun shield block out the infrared light so that the scientific instruments behind the mirror only see the infrared light from the objects in the universe that we wish to observe. So the entire telescope is cooled down via this sun shield to an incredibly cold temperature of minus 390 degrees Fahrenheit or minus 235 degrees Celsius, just 40 degrees above the coldest temperature that space can have. Once Webb launches on December 18th, it will then take 6 months to get to its orbit and unfurl in a very complex sequence where every step has to work perfectly. So we should have our very first images ready to share with you 6 months after launch, or maybe a little bit earlier, maybe about 4 months after launch for some of the first test images. So come around April or May of next year, we should have images for you of the first James Webb observations. And then science operations should begin around June of next year. The planned mission lifetime for Webb is at least 5 years. So all of the mission critical hardware has a second copy to guarantee that it works for those 5 years. But if all goes well, we hope that it will work for at least 10 years. That's how much fuel it has to keep in its orbit. But we might be able to stretch a few more years out of it. Fingers crossed. And the last thing that I just wanted to mention is that Webb is a truly international mission. It's a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. In total, 14 countries have contributed to building the telescope and the scientific instruments on board. Right now, Webb is currently on a boat to the launch site in South America. It is going to launch from French Guiana, where the European Space Agency has a launch site. And the reason that it's launching from there is that it's right on the equator, so it's a perfect launch site for rockets. And that will be one of the main European contributions to the mission, actually launching it into space. So it just passed on the boat through the Panama Canal a couple of days ago. So keep an eye out on the news for when it arrives at port in French Guiana. So to summarize, Webb will tell us about the very first stars and galaxies in our universe. It will tell us about how those galaxies evolved over time to reach their current state. We will be able to study how stars are born, what happens during their lifetime, and how ultimately they come to their fiery end. And finally, we will learn some truly deep insights about planets orbiting other stars, including, for the first time, searching for signs of alien life on exoplanets. And with that, I will be more than happy to take any questions that you have.
That is fantastic, Dr. McDonald. Thank you so much. It's such an interesting time to be alive and to be exploring in space. So we're going to take a look into the Q&A section of our Zoom call, and I'm also going to check in with Imani and see if we have any questions on our Facebook too. So if anyone who's still on our Zoom call or anyone who's joining us on Facebook, if you have a question, go ahead and put it into the Q&A, or on Facebook, you can type it into the comment section and we can get the questions from there too. But we do have 5 questions ready to go for you. So, oh, we have 6 now as well. So we're going to start with the first one and go through the list. So the first question is from Yeffy. Is empty space composed of plasma?
Oh, that is an absolutely great question. So for anyone who hasn't heard, plasma is a 4th state of matter, distinct from the gas, liquids, and solids that we're used to. So plasma is an ionized gas where the electrons are free to roam. So indeed, most of empty space that we see is made of plasma. So when that event reionization happened 13.5 billion years ago or so, that was the moment where the universe changed from being a neutral gas to being a plasma. But space is still pretty empty, even though there are electrons and protons flying about. They're quite dispersed, but absolutely, plasma is all throughout our universe.
All right. The next question is, when can we expect Earth to reach Milky Way galactic core? Or will it ever reach Milky Way galactic core?
Well, fortunately for life on Earth, we're not traveling towards the core. And that would actually be really bad for us because there are really high energy stars close to the core. And there's strong radiation like X-rays coming from the gas and the black hole towards the center of our galaxy. So we're actually in a region that you could imagine as the galactic habitable zone. So we are orbiting around the center of our galaxy, just like the Earth orbits around the sun. And here's a cool fact. Because we are orbiting around our galaxy, when the dinosaurs were alive about 200 million years ago, the dinosaurs were actually alive at the opposite end of the galaxy to where we are right now.
That's an amazing thing to think about. All right. I never thought about that before, how far around our galaxy we've traveled since the time of the dinosaurs. It's amazing. Next question comes from M. Smith. Does the telescope make the chemical analyses, or does that happen in your lab?
That's a fantastic question. So when any telescope that does spectroscopy observes an object, the data that we get down to Earth still needs a lot of processing to figure out what is going on. So we receive, you can imagine it almost like a series of images that the telescope has taken at different colors, but then we have to run computer models to then figure out what it means. So during my own PhD, I developed a computer program to convert telescope observations into information on what the molecules are in an exoplanet atmosphere. So there's a lot of computer modeling that goes on to do this. And as part of that, we do use information from laboratories that helps us to figure out where the signatures of each molecule lie. So yeah, it's unfortunately, Webb doesn't point at an object and say, Eureka, there's water there. It takes us a few more months of work on our computers to figure that out.
Right. Another question that ties into that, do you use the chemical analyses to redirect the telescope to look somewhere else?
Oh, that's a fantastic question. So whenever we have a telescope like the Hubble Space Telescope or the James Webb Space Telescope, often plans change over time as we learn more about our universe. So every year, astronomers like myself get together and we write proposals for objects we would like to observe in the universe. And then other astronomers then read our proposals entirely anonymously, rank them, and then that decides, based on the feedback of the whole community, which objects we want to look at. So if we find something very surprising because of a chemical analysis, like for example, we find a rocky planet that looks like it could have a biosignature, then in the next year, astronomers can propose to look back at that object and try and confirm it. Or if it turns out that an object is boring, for example, we find a planet that is completely shrouded in clouds, so we can't see its atmosphere, then we can use that information to decide what planet we should look at instead. So absolutely, we continuously adjust the science that we're doing based on what we have found so far.
All right, wonderful. And we do have a comment in the chat from Alex saying, thank you, Professor, for giving this wonderful, interesting presentation to the Newark Museum of Art and our audience as well. All right, thank you, Alex.
Thank you very much, Alex.
All right. So another question, we mentioned how the James Webb is going to be out at the L2 point, where it's not going to be serviceable. Someone asked the question if it has components that can be upgraded like computer programs.
Okay. So software uploads can absolutely be done. And we actually had an issue in the last year with the Hubble Space Telescope where there was a big problem with one of the computers, and parts of it had to be reprogrammed and then uploaded to fix it. So software patches can absolutely be done, even though we can't get up there and upgrade the hardware like we could with Hubble. So, and indeed, we are expecting after the launch to figure out new ways to process the data. So we may well be able to figure out clever new ways to tell James Webb how to observe an object. Actually, one specific example for exoplanets. With Hubble, the Hubble Space Telescope launched before we knew any exoplanets existed. So it has been a learning process, just figuring out the right way to do that. So when we started in the 2010s, we took Hubble and just stared at exoplanets. And the data we got was not really that good because it wasn't designed to do exoplanet science. But then we figured out that if instead of staring, we took Hubble and kind of caused it to sweep across the star back and forth, almost like a typewriter, we could actually look at much brighter stars and hence obtain much more sensitive measurements of exoplanet atmospheres. So it's certainly possible that we'll be able to reprogram parts of James Webb coming up with clever techniques to do our science better.
Great. And this kind of goes along with that question too, since we're talking about upgrades. Does communication change over a year as the Earth orbits around the sun, since we're going to be in different orbits from the James Webb?
So I actually have a bonus slide on the how James Webb communicates. So if I can have permission to screen share for a moment, I may be able to actually show a diagram that will illustrate this. Okay, thank you. Okay, let's find where the bonus slide is. Come on, see. Okay. Okay, here we go. Going past it. So, in short, the answer is that there's a series of telescopes, receiver stations on the ground and relay satellites in orbit that constitute something called the Deep Space Network. And this is what NASA uses to communicate with all of the missions in our own solar system. And so this is used to maintain continual communication with missions like Hubble is a little easier in low Earth orbit, but for example, the Voyager spacecraft or New Horizons, objects in deep space. So this is how continual communication will be maintained with Webb.
All right, great. Another question from an anonymous attendee asks, what % chance do you think life exists in our solar system? And what % chance do you think intelligent life exists in the universe?
That's a fantastic question. In our own solar system, I think it is almost certain that there will be life on one of the other planets or moons, partly for the reason that we know that there is plenty of rocky material that is exchanged between the Earth and Mars, for example. So we have plenty of Martian meteorites on the Earth, and there's even been some signs of rocks seen by the rovers on Mars that look like they might have come from Earth. And we know there are microorganisms that can survive in the vacuum of space, like tardigrades. So I would be very surprised if some Earth life hasn't already made it to Mars. Or indeed, life could have started on Mars first, 4 billion years ago, when Mars was a habitable planet, and seeded life on the Earth. So perhaps the more interesting question in my mind is whether there is life in the oceans of some of the icy moons like Europa and Enceladus in our outer solar system. Because they have a layer of ice shielding that ocean, if we find life down there, it should be independent life that started on its own. So if we see some kind of, alien dinosaur swimming about in the oceans of Europa, that's what I would really love to see. And as to the second part of the question about intelligent life in our universe, that's tricky because, of course, the search for extraterrestrial intelligence has been looking for signs of radio emissions from aliens for over 50 years now and has not found any yet. We have also done searches looking for large structures called alien megastructures. For example, if aliens build a large collection of solar collectors around their star to create something called a Dyson sphere, and we haven't found any signs of these yet. So my personal thought is that simple life, like single and multicellular life and animals, is probably common throughout our own galaxy and our universe, but intelligent life is probably reasonably rare, at least in our own galaxy, because you can actually run some calculations and work out that if aliens are capable of traveling between stars, it only takes them around 10 to 100 million years to explore the entire galaxy, and we haven't found all of their leftover spaceships or debris or anything yet. I really hope that there are intelligent aliens out there, and Webb will actually enable us to search for signs of things like industrial pollution in the atmospheres of exoplanets. So I hope they're there, and we will look, and fingers crossed, we'll find the aliens eventually.
All right, I hope so too. So we have time for maybe two more questions. So one question is, how many exoplanets have been discovered to date? Do we have an accurate number?
Yep, so the rough number is 4,500. If you give me a couple of seconds, I will get up the NASA Exoplanet Archive and give the exact number as of today. Is 4,528. But
wow.
we also have another 4,500 candidates that we are waiting to confirm.
Good gracious. So that's almost 9,000, a little bit over 9,000 exoplanets.
Yeah, we've found
amazing.
a lot of them. And incidentally, I should say, for any of you out there that want to help us find some planets, there's a website called Planet Hunters that you can use that will teach you how to use data from NASA's Transiting Exoplanet Survey Satellite, TESS, to use your own eye on the data and search for the little dips caused by planets. And ordinary citizen scientists have already found some planets that our computer programs entirely missed. So if you're willing to help us out and find more planets, please try out Planet Hunters. And if you find one, you'll even get to join the scientific paper announcing the discovery.
All right, fantastic. And this is one question that I have that someone else put into the Q&A as well. What about any special websites where we can see pictures that are from the Webb, from the telescope itself?
One of the things I really love about NASA is that all images and data they create becomes publicly available, and it becomes publicly available and is hosted on a website, and it's completely transparent. And that's true for all of the missions, like the Mars rover surface photos, for example. So I don't think the website is currently up for the Webb photos, but if you search, for example, for like NASA Hubble photo archive, you'll already be able to find all of those. So check it out around about 4 months to 6 months after launch. That will be where they will first appear. And in terms of the scientific data, it depends on the program. So observations like my white dwarf planet proposal, since we put so much work into proposing to get telescope time, we usually are given a little bit of a head start. So in my case, I will have the data for my program for 1 year before it becomes automatically publicly available. But any large programs on James Webb, so anyone that asks for more than 75 hours of James Webb time, all of that data is instantly available publicly as soon as it is taken.
All right, fantastic. And unfortunately, that means that we are now out of time. So I want to personally thank Dr. McDonald, Shelley from Languageers, Rebecca from Automated Sync, and Imani for being a part of our program today. Imani, can we bring up the final slide so that people can see Dr. McDonald's contact information? So if we didn't get to any questions, or you may think of something after the presentation is done, Dr. McDonald has given us his Twitter handle and YouTube page that you can visit. He says you can tweet at him all you want because he loves to answer questions. So if you have any other burning questions or are asking more about James Webb as we come closer to launch or closer to some of the first images being released, please go ahead and contact him as well. All right, so Imani, let's go to the next slide here. So we want to thank everybody for joining us, but this weekend we have 2 in-person events that we are hosting at the museum. On Saturday, October 9th at 6 p.m., we have our community night, which is a free block party. We have a live DJ, a fashion show, the premiere of the Philip K. Smith III's permanent installation, and much more. So we hope that you enjoy it, that you can join us in person for that block party on October 9th. But then also on Sunday, October 10th at 1 p.m., we have the showing of the movie Stingrays, which is about the Newark swim team. And so this is in the museum's Billy Johnson Auditorium. It is free, but you do need to register for it because we are limited to 75 people that we can allow in our auditorium at this time. Let's go to the next slide. So we want to thank you all for joining us. Remember that you can support artist projects at the Newark Museum of Art through our annual fund. So you can donate to us if you want to learn more about that, or you want to find out how to get more involved. You can contact Michelle Saliola, who's the Director of Individual Giving and Membership. So let's take away our PowerPoint, bring our guests back so that everybody can say their goodbyes as well.
Well, thank you very much, Mary, Imani, Shelley, and everyone for making this fantastic event happen, and for all of you listening. And I just really can't wait to share all of the amazing results that we're going to find. And I should say that as astronomers, we are really terrible at keeping secrets. So if we do find aliens, like you'll probably see it on Twitter before the paper is even out. So we're just really excited to get all these results out to you. It's been a long time coming, and this telescope is truly going to change the way that we see our universe.
All right, so thank you so much, Dr. McDonald, and thank you, Shelley, as well. It's a pleasure having you here. So for everyone out there, we hope that you enjoyed Ask an Astronomer today and wish you a very pleasant rest of the evening. So goodbye, everyone.